So today already we have a lot of sessions with this OpenFOAM, which discussed about this fluid dynamics concepts. And from the title, I can say already for the multi-phase flow part, it will be discussed in a very broad manner by Professor Chandan in the further sessions. So I would like to quickly tell about that how a non-Newtonian fluid can be incorporated with this multi-phase flow. So for that, already we have, first I will show it this slide with the from where these motivations come. So if we start with the we are trying to see in the morning session, I have heard about Professor Suman Chakravarti that in a simple pipe also we can see a lot of things. So with respect to Newtonian, we are seeing a lot of things. So initially we started with a single phase flow with a non-Newtonian concept only, and later we shifted to a multi-phase flow section also. So today we will be discussing how we can incorporate this to non-Newtonian fluid in a two-phase flow. And basically the whole discussion talks about a microfluidics concept. So, and in the further session slides, you can see how the changes has been made once we are moving from Newtonian to non-Newtonian concept. So quickly I will tell a little bit of the multi-phase flow basics. So already we have seen about some particles talk in the morning session. So our talk will be, my talk will be basically only liquid system. That is oil and water. So I am dealing with this oil and water system. So there are many challenges with this multi-phase flow. We can see that the main concept that comes is the interface tracking. If we are having any two-phase simulations, so interface tracking is one of the main aspect. Then how the phase interaction is taking place. At the same time, as it is very difficult to see what happening when the complexity of model increases, and at the same time we can have some numerical instability also. So we are going to see into these aspects in the further slides. So already we have seen this. This is an open toolbox, and this can be used for various flow problems, which is customizable, which is already discussed in the past talks. With it has having extensive libraries, and I have taken the snapshots so that this can be useful for the researchers or the students who are in the initial phase of their this study. Which this is from the tutorial part. We can see there are the different categories of solvers we can have in this OpenFOAM. Among these, so we are getting into this multi-phase solvers, which comes with different different criteria of solvers. So again, among these, we are getting into this interFOAM, which is which is used for two incompressible fluids, isothermal, which uses the VOF method for this phase interface capturing. So once, so the first step with that in the tutorials, we are having the case directory, and after that we are going for the any kind of geometry, and that is accompanied by the creation of the mesh. Then after the mesh, we are going to define the fluid properties. That is the main part we can see where we'll be defining our these non-Newtonian properties. Then comes the how to set up the multi-phase flow, then how to run the simulation, then comes the post-processing, then validating and verification, and after that troubleshoot and refine. If there is an issue with the validation, how to troubleshoot, and we can refine our results. So coming into the setting up of the non-Newtonian environment, so within this interFOAM already discussed, there we have different 3 different directories. So within this constant folder, we can have the transport properties. So this transport properties takes care of the different, whatever the different kinds of fluids we are going to use in our problem. So that can be all the physical parameters can be passed into this transport properties, where so here we can edit the transport properties file. Here only we can have the different non-Newtonian models, and we can set the model parameters also. Now coming into the structure of the transport properties. So this can be useful if someone is starting from the scratch. So I have taken the snapshot from our this transport properties. So here we can see since this is a two-phase flow problem. So here we have two phases, water and oil. And this water, the transport model, you can see for the both cases is the Newtonian. So here, this is the place where we can change the model from Newtonian to non-Newtonian. And in non-Newtonian also we have different categories. So this is the crux where if somebody wants to change the fluid parameters, so here we can edit the model. And we can choose appropriate non-Newtonian model, and we can edit the file according to our application or requirements. Now coming into the transport model, so we have viscosity models. Different viscosity models are already available in the libraries. The first one is the Bird-Carreau, Cation, Cross Power Law, Herschel. Different viscosity models we have. So already told, according to the requirement, we can implement any of the viscosity model. And in case if somebody is doing any experimental, so those from the experiment also we can do the rheology of any fluid, and we can do a fitting analysis, and we can fit into the appropriate viscosity model. So basically the most commonly used the power law model. So we can see how this power law model is available in our this viscosity model. So in the last slide, I have shown where we can the water and oil, both were taken as the Newtonian fluid. Suppose if I want to change the one of the property to some power law model, so this should be edited. We can see in the power law model, this is the transport model, this is the power law. If it is a Newtonian, so in the last case it was Newtonian, and we have to define this power law coefficients too. In this case, we have two different parameters, that is the nu max and the nu min. This can be taken if it is an experimental part, so it can be taken from the rheology of that particular fluid, and then the consistency index and n. This both can be taken from the rheological parameters, or if it is for any validation part, so we can take from there also. Similarly, we have one more different models we have, but due to the interest of the time, I will just discuss about this Bird-Carreau model. So the most common approach to model any non-Newtonian is the power law only. But this power law doesn't sorry, this model unrealistically, because power law doesn't discuss about when we have a very high shear rate and when we have a very low viscosity. So in order to incorporate very high and lower viscosity range, so this Bird-Carreau model can be an effective one, and this has been reported in the literatures also. So here, if somebody wants to incorporate the Bird-Carreau model, so like power law model, here we have Bird-Carreau coefficients, and here like in the previous case, it was having the maximum and minimum. Here we have the nu naught. So means this is the zero shear rate viscosity, and nu infinity is the infinite shear rate viscosity, and K and N. So similarly, if somebody wants to incorporate Herschel-Buckley or other models, so they can directly use this model. So this is available already. I have given the reference from where I took. Now coming to the editing of this transport file. So you can see here I have changed suppose if I am using this water, means this water, if we are using some any non-Newtonian fluid like xanthangum, so it has been named as a water, but we are modeling it as a power law. So here we can make the changes. So here I have marked this has been modeled as the power law model, and the oil is as Newtonian only. And both, if somebody wants to use both as a non-Newtonian, then again here also some power, another non-Newtonian model will come into picture. Now, so in order to see the case whether whatever we are implementing, whether it is working or not, so we have taken one reference from the literature from this Carello, and we have taken a simple T-junction problem. For the same, we have all the physical parameters are given, and this has been taken from this Carello. So, and you can go through these papers for further all the geometrical aspects. So, this is a simple T-junction problem where they are creating a non-Newtonian droplet. And the same thing we try to validate so that we can see how it is changing from the Newtonian case. In the next case, so these are the governing equations that has been used in order to solve the problem, the continuity, momentum, and the transport equation. So here, this mu is being modeled for the non-Newtonian case. This will be modeled according to the whatever the model we are incorporating into our problem. Next, I will directly show you some results. Here you can see the first part, you can see that is the for Newtonian fluids I have shown. This is a simple T-junction problem where we are creating oil, this water in oil. Means we are creating the water droplet in a oil system. So we can see the trend as the capillary number increases. But at the same time, we have taken the same model, and all the geometrical parameters were same, only we went with the non-Newtonian case. So here we can see for a shear thinning fluids, we have got a similar kind of trend, but with some different insights. So here, with respect to Newtonian, when we are moving with the shear thinning fluids, the droplet size were comparatively smaller than that of the Newtonian one. And at the same time, because of this non-Newtonian property, even we can see a different phenomenon as compared to the Newtonian. If I can compare the last case, here we can see there is a filament. We can see when there is a droplet, breaking is taking place. So we have just started with this non-Newtonian system. So and this was the validation case. So we have seen different phenomenon that is occurring, which is not seen in the Newtonian fluids. And the same thing,
Rakesh, could you please conclude the results?
Yes, sure. This is the last slide. So, and even we have gone for the verification, and we got a very good comparison between this Carello and whatever the model we have taken this to model this one. Now, I would like to summarize. We have shown how we can incorporate these non-Newtonian models for these multi-phase solvers. At the same time, we have shown the transport properties file for setting up the simulations with the available models. And for this current model, I have used this power law model. We have shown a qualitative and quantitative comparison for this non-Newtonian case. And one more thing, as we are doing the simulation, we found that there is an increase in the computational time compared to a Newtonian system, and that was with a reasonable limit. So because of this complexity of the fluid and all the rheological parameters that is coming into picture, so there was a increase in the computational time as compared with the Newtonian system. So with this, I would like to thank IIT Kharagpur and this Param Shakti that we are at IIT Kharagpur. Thank you.
Thank you, Rakesh. This was very nice talk. So I request you to please have a look at the chat. If anybody has asked any relevant question to your talk, you can answer in the chat box.
Okay, sure.
Okay. Thank you for joining. So we have 2 remaining training sessions now, which will be lasting half an hour each. So the last hour. And the fourth training session is on introduction to multiphase flow, but you have already seen in Rakesh's talk on an advanced multiphase flow problem where liquid-liquid interaction is happening. So for this training session, because we had to reduce the time to half an hour, um, I mean, we have also reduced training content a bit. So I request Mr. Biraj Khadka who is a research associate at IIT Bombay and he works with FOSSEE. So he will be presenting some basic introductory tutorial on multiphase flows in this training session. So Biraj, could you please try to share your screen?
Okay, sir. So can you share? Can you see my screen?
Yes, please share your present. Yeah, we can see your presentation. Right. Yeah, please go ahead.
Good evening, everybody. So my name is Biraj Khadka. I'm currently working as a part-time research assistant at CFD FOSSEE here at IIT Bombay. Today, I'm going to talk about the bubble write simulation using VOF techniques using the interform solver. So regarding the multi-phase modeling, there are two kinds of phase flow, namely continuous phase flow. This occurs when both the phases have higher volume and the sharp interface. We can take an example of surface flows like in a river or sea, and also the dam break simulation. And another one is dispersed continuous phase. This occurs when one phase has lower volume fraction compared to other and smaller, which is dispersed particles make it diffused in domain. For an example, the spray, where liquid droplets is a dispersed phase, whereas the air is the continuous phase. There are multiple solvers available in OpenFOAM for the multi-phase modeling, namely interform, two-phase Euler form, intermixing form, reacting two-phase Euler form. So interform solves for only two incompressible isothermal immiscible fluids using VOF methods, whereas multiphase interform solves for more than two incompressible isothermal immiscible fluids. The equations it solves are the continuity equation and momentum equation. So here the rho is the effective density, which is a linear combination of two phases, and also u is the effective velocity, which is also the linear combination of the two phases. So if there is a phase air and water, so u equals to rho u1 plus 1 minus alpha u2. So we will get back that later. And where rho represents the density and u is the velocity, and g is gravity if there is a if there is gravity acting downwards, and fs is the surface tension force between the two fluids. So in interform, it solves the volume fraction transport equation. So here u is the effective velocity. So if let's say u1 is the phase 1 and u2 is the phase 2, so if in one cell the alpha is equals to 1, that means volume or fraction of phase 1 is 1. That means u equals to alpha u1 plus 0 into u2, where u equals to alpha u1. So and when alpha is 0, then u equals to 0 into u1 plus 1 into u2. And this is the volume fraction transport equation, where uc is a compression velocity. If c alpha is equals to 1, it represents the sharp interface between the two fluids or phases. And today we are going to discuss about the bubble write simulation, where we have a water column of dimension as shown, and the dimension is 30 millimeter by 12 millimeter, and at 4 millimeter height there is a bubble. Inside bubble there is a air, and also at the height of 24 millimeter there is an air cavity, and rest of them is the filled with water. And this is pure gravity driven, and no additional force is considered. So for the block mesh dig, we define the 8 vortices starting from 0, and the numbering is as shown, which has distinct coordinates. So regarding the case structure, inside the VOF bubble and zero directory, we need to mention the boundary condition for U, which is the velocity, and the pressure without the hydrostatic effects, PRGS, and the volume fraction of the water. And inside constant, if we need to define the gravity, then we need to also use the G file. And depending on the type of flow, be it laminar or turbulent, we have to also mention it inside the turbulence properties. And finally, in transport properties, there are, so we need to mention density, surface tension, and viscosity of the fluids. And for the mesh, we need to define the number of divisions, coordinates, patch name, and the blocks inside the block mesh dict. And for the inside the control dict, we can define the start time, end time, time step size, and the functions to calculate the force coefficients and so on. Inside the finite volume schemes, we can mention the different discretization scheme for convection term and divergence term, etc. And inside the finite volume solution, we can define the smoothers, solvers, and relaxation factors, and so on. Another difference from non-multiphase solver setting is the presence of the set fields. So we can initialize the fields for different fluids inside the set fields dict. So in our problem, there are two patch, namely atmosphere, which is exposed, the top face is exposed to the atmosphere, and the rest of them are walls. And regarding the boundary condition, there are two patches, and for the velocity, pressure inlet outlet velocity is applied, where pressure is applied at the boundaries, and it is same as zero gradient for the outflow, whereas for the inflow, the velocity is same as the internal cell value. And for the walls, the no slip is applied on the walls because the velocity will be zero on the walls. And for the pressure without the hydrostatic effects in the walls, so we define the fixed flux pressure, which is also a zero gradient, and it adjusts or it fixes the pressure gradient such that the flux is calculated from the velocity boundary conditions. And value uniform zero means it is initializing. It is just for the initialization. And inside the atmosphere, the total pressure condition is applied, where P naught is uniform zero, and the pressure at patch is calculated from this formula. Lastly, for the alpha dot water, which is the volume fraction of water, in the walls, zero gradient is applied, which in case of the multiphase means that the liquid can pass through the wall. And in the atmosphere, inlet outlet condition is applied. So which means it is very flexible boundary conditions. So in case of reverse flow, the alpha dot water will be 0. Let's talk about the set fields. So initially we initialize the whole domain, whole water column with the water. So for that, we have to define inside the default field values and set the alpha dot water as 1. So the alpha can't be greater than 1. So that is the maximum. So that means the whole domain is filled with water. So in order to define the air in a particular region, so we have to define inside the regions. So for in order to define the cylinder type of region, we have to define cylinder to cell, and for that, we need to define 2 points and radius. So in this case, the radius of 2 millimeter bubble is defined, and within this region, or within the cells within this region, will be initialized with alpha dot water as 0. That means 1 minus alpha. 1 minus 0 equals to 1. So that means the volume fraction of air will be 1. Similarly, to define the box, you need to define it as a box to cell. So it is, so if you, as John sir has already mentioned, if you don't know any like syntax, you can use banana or any names, and whenever you run the simulation, it will throw an error and give the options to put in, and you can set accordingly. For the box to define, we have to define the extreme points of the box, and similarly, the alpha dot water will be 0. That means the cells inside this box region are initialized with air and not with water. And inside the transport properties, we define the fluid properties like density, viscosity, and surface tension. So so the density of the water is taken as 1000 kg per meter cube, and for the air, 1 kg per meter cube. So the phases are water and air, and inside the water, the Newtonian fluid is used, and not the non-Newtonian. So, and also the nu is 10 to the power minus 6, and the density is 1000. And for the air, similarly, its properties like viscosity and density is defined, and sigma is the surface tension. So between the air and water, the surface tension is 0.07. So inside the control dict, we have to define the application or the solver name, which is interFOAM, and the start time is 0 and the end time is 0.3. The delta t is the time step size, and the run time modifiable means it ensures that we can change the settings, solver settings, during the runtime, and the right format is binary. So all we need to use the command is block mesh, so which generates the mesh and create the blocks, and to set the non-uniform initial field for the phases, we use the command like set field. And finally, to solve all the governing equations I mentioned previously, so we have to run the interFOAM command, and it will solve. So the results after running the simulation is kind of like this. So the bubble is here, and it rises because of the density difference. Due to the lighter density and buoyancy, it rises up, and it gets coalesced with the air gravity at the top. And this is the static mesh. So it doesn't change. The number of cells doesn't get changed, doesn't get refined at every iteration. So this is hence its name is static mesh. But if we need to like simulate with the adaptive mesh refinement, AMR, so we have to use extra dictionary, which is dynamic mesh dict. So all we need is just this file. So where refine interval means that the mesh will get refined at every iterations, and depending upon the value of field, which is alpha dot water, which is volume of fraction of water. So and the mesh will only get refined if the value of the alpha dot water is between the 0.01 and 0.9. And we have used the number of buffer layers as 2 and the maximum refinement as 3. And I have mentioned maximum cells as 60,000. So if the maximum number of cells gets exceeded 60,000, then the refinement will get stopped and get constant at every iterations. So this is a dynamic mesh. So as you can see, like at every iterations and at the interface between the 0.1 and 0.9, so there is a refinement going on. And also here you can see at the interface. So that is the domain of interest in the multi-phase flows. So that is the domain of interest, and it is complicated to model. So this AMR saves our time and increases our efficiency. So I will also demonstrate like So actually, I've already ran the simulation, but in order to clean the tutorial, we have to use this command, foam clean tutorials. So what it does is it clean the case, and this 0.01 to 0.3 gets deleted, and it get initialized. So from the start, I've already told you the command. So first, what we do is block mesh that generates the mesh. So the patches are walls, atmosphere, and the default faces. And the number of cells is only 50,000. So I'm only demonstrating the static mesh for the bubble right simulation. And after that, what we do is we set the fields. So in order to do that, we use the command set fields. So first of all, the alpha water is initialized in the whole domain, and we have also mentioned or defined the cylinder and the boxes, and in that the alpha water will be 0. And lastly, interfoam command is applied. So this may take few minutes, but I will surely share the case file with you guys. And as an assignment, also, like as in your home, like you can do the simulation of 2 bubbles and see how it goes. But this takes like few minutes. I have also this is the same files. Actually, like in the case of static mesh, the mesh doesn't get changed. So you can see there is no any change in the number of mesh. But in case of dynamic mesh, like AMR, the mesh will get changed at the interface location. So it remains same as it should be. So the alpha water. So I will put the surface, and from the start, how it goes like this. So the shape of the bubble gets changed due to a lot of forces like surface tension and density. Finally, it gets coalesced, and this is how the simulation works in OpenFOAM by using the interfoam. So if you guys have any questions, please let me know. And yeah, if you have any doubts, you can even mail me at this email address. So yeah.
Thanks, Biraj.
So
I think we have a couple of minutes to take a few questions. So let me see in the chat box if there is any particular question for you. So someone is asking, can overset mesh be used? So I will discuss about overset dynamic mesh in the upcoming next training in detail. But I don't see any particular usefulness of overset mesh for this volume of fluid problem, which I'll discuss in detail for which cases we should actually use overset mesh. So there is another question by Sujata. Amongst inter-isoform solver or inter-icoform, I think, solver in OpenFOAM ESI version and interfoam in openfoam.org version, which one do you prefer to solve multiphase flows?
Actually, like I don't know about like inter-isoform. I've never used it, but regarding the this continuous phase, I generally prefer this interfoam solver.
Yes, so I think there is, in terms of their solution algorithm, there is not much of a difference. It's almost the same volume of fluid equation solved. So it will be a good exercise for you to compare quantitatively the results of this tutorial running by 2 solvers. But I don't think there will be much difference if you use the same maze and everything, same solver setup.
Actually, this interfoam solver uses MULES, multi-universal solution limiter for explicit solution, but it might be different for inter-icoform. So you need to check the results.
Right. Yes. So another question we have before we stop this training session is that can we merge this solver for CHT phase change for BTMS immersion cooling rather than homogeneous mixture than ICO-foam? Do you want to comment?
I think I don't know about like CST, but people have used incorporate the transfer equation in the ICO-foam. So yeah, that's all I know.
Yeah. If John is present, if you have any comment, you can post in the chat box to this question. All right, so let's move ahead. And I really thank Biraj to take it over this training session over a short notice. And it was supposed to be a joint training session by both of us, discussing more lot in details about adaptive mesh refinement, but you can see that our time is limited and we had to restrict it to half an hour. So I thought I will discuss the dynamic meshing part in the next training anyway. So thanks, Biraj. Thank you.
Thanks.
Thank you for sharing the training with us. All right, so we have one last training session left, which is by me on the dynamic meshing and the usefulness of different dynamic meshing techniques for external aerodynamics and fluid structure interaction problem. So I hope that you will keep joined with me and I will try not to bore you much in this half an hour session. So let me try to share my presentation. No, I don't think it's sharing. Can you see my presentation?
Yes, sir.
All right. Okay. So I hope that it's in full screen. And due to the settings of the Teams, I can't see the chats while I present. So I request you all to bear with me. So after my presentation is over, I can go through the chat and try to answer some of your questions. Okay. So basically, this last session of the training was designed to give you the overview of different dynamic meshing strategies, mostly to be used in the external aerodynamics and fluid structure interaction problem. And I will try to give you a brief overview of all the different possible dynamic meshing strategies that we have available in OpenFOAM. And mostly these are available in all three different forks of OpenFOAM, like openfoam.com, openfoam.org, and also Foam Extend. So just to sum up, in this training session for this event, we tried to give you an overview of first on different post-processing techniques, such as particularly using Python, and how do you do advanced post-processing just using Python libraries and commands. Then we actually give you a training session on an advanced meshing technique using snappy hex mesh and different tips and tricks to improve your meshing if you want to use snappy hex mesh. Then actually we went through some basic introductory simulation of heat transfer. And just before the training by Biraj, you saw some basic introductory training on multiphase flow using volume of fluid method. And then this training session, the fifth training, will sum up the other aspect of it, which is the aerodynamics and fluid structure interaction part. And this is the field where we mostly need our bodies to move with high amplitudes. And I will come to the fact that why we need different type of dynamic meshing strategies. So without further delay, I have already introduced myself. I'm Chandan, and I'm an assistant professor of aerospace engineering in the University of Birmingham. My research interests broadly lie in the areas of unsteady aerodynamics, nonlinear dynamics, and fluid structure interaction. And I would, before I go through the training, I would like to acknowledge my collaborator, Dr. Joel Guerrero, whom probably you all know. He is the CTO of Ulf Dynamics, and he's a very active contributor to the OpenFOAM training sessions. So we both are actually in the OpenFOAM technical committees, and some of this training material are prepared in collaboration with him and with the tutorials available also in his websites. Um, so I actually had a research laboratory called Bio-Inspired Fluid Structure Interaction Laboratory in the University of Birmingham, and where we do mostly research on fluid structure interaction. Now, coming back to this training session, there are two main references, and I have given here the links, and later I will post it in the chat box, which is a great place for you to start for any type of any aspect of OpenFOAM simulation. So the first link is the tutorial wiki of OpenFOAM, and the second one is the tutorials provided by Ulf Dynamics. And these are really two great resources, along with the website of Professor Hakan Nilsson, who actually gave a keynote talk yesterday. So anybody who is a newbie in OpenFOAM simulations, please note these links. They are really helpful. Right. So what is the agenda of today's half an hour training session? We will first look into what are the dynamic meshes. We will see few examples of dynamic meshes, such as what is mesh morphing, what is known by overset meshes, what are the moving meshes, what are sliding meshes, and what are the adaptive mesh refinement. So these are the five major different class of dynamic meshing strategies that are available in the object-oriented programming of OpenFOAM. Now, due to the, again, restriction of time, I will mostly talk about mesh morphing and overset meshes, but I will just show you some glimpses of the other three types. All right. And some logistics about this presentation is that, again, there will be no hands-on session because, as you can imagine, it's difficult with so much large audience to do a hands-on session. So it will be a demonstration. However, I will again share these case files with you if you would like to try it later. And my contact will be there for you to reach out if you have any problems in understanding. Right. And this is a beginner level introductory training session, and the present tutorial cases are tested for the ESI OpenCFD versions, version 2306. However, they are almost the same for the .org version with a slight changes in the syntax. Particularly for the version 11, you need to know some different syntax of it. You are not expected to run any cases during the session, so it's a demonstration, and feel free to post your queries in the chat box. Now, what are dynamic meshes? Let's start with this understanding that uh, dynamic meshing strategies allow mesh motion. All right, so now I think you have got this clear idea with these 2 days of different talks that our CFD simulation needs three different steps. One is pre-processing, which involves making the geometry and preparing discretizing the geometry in different type of meshes, may it be structured, unstructured, or hybrid meshes. And we need some sort of strategies to allow this mesh to move for accommodating the moving bodies or deformation in the structures, right? Now, as Professor Suman Chakrabarty told today, that whenever we do such operations, we need to first understand what changes we are incorporating in the governing equation, all right? So if you see this governing equation, this is a generic transport equation where we have, along with other unsteady term, diffusion term, source term, we have a term which is the convective term. And within the convective term, you can see that we have to incorporate the relative velocity between the fluid and the mesh velocity UG. So this is the main difference when we try to incorporate dynamic meshing strategies for body movement or deformation of the body. All right. Now, how can we achieve this mission, this mesh motion? As I said, it can be achieved by morphing the mesh. By morphing, it means that the cells or the cells volumes will be deformed. So there will be volume changes in the different cells when we morph the mesh. We can either add or remove new cells. We can slide a certain region of the mesh. If particularly we have a rotating component, we can do it by using arbitrary mesh interfaces. Also, we have an interesting concept of disconnected meshes, which is called overset meshes. I will come in details what are these these meaning actually. So the key takeaway point from this slide is that these dynamic meshes algorithms, they are not actually restricted by any physical models, which means that if you actually want to solve heat transfer problem or multiphase problem or fluid structure interaction problem, your dynamic meshing strategies should be compatible with all these physical models. So they are model free in that sense. Now, as I was already discussing that why we need dynamic meshes, we need dynamic meshes particularly for this kind of problems if we want to simulate. One is prescribed body motion. That means, for example, the first example you see an example of mesh morphing where we are giving a prescribed motion to a cylinder to translate up and down. And to incorporate this body motion, we are deforming our meshes where the cell volumes are changing, right? We can also incorporate rigid body motion, which is basically we can move the whole mesh. I will show you the example without even deforming the mesh. We need these dynamic meshes to simulate fluid structure interaction problem. And also we need it for, as you have seen in the previous training and the previous talk, that we can do it by adaptive mesh refinement based on a scalar variable. All right. So in the picture animation, you see three animation. The first animation, as I said, this is representative of the mesh morphing, where our mesh is deforming due to the body motion. The second example is actually an example of a sliding mesh, where you can see that one component, the inner component of the mesh, which is a circular component, is actually sliding over the outer static component, and the interface between these two mesh regions are called arbitrary mesh interfaces. Okay. And the third example, as I have already told you, that this is actually an example of adaptive mesh refinement, where my mesh gets divided into smaller cells depending on a criteria which is given with a target scalar variable that we want to capture. All right. Okay. So OpenFOAM also has a overset mesh capability, and but the older versions of OpenFOAM didn't have it. So this is relatively a newer addition as a mesh motion strategy. And here you can see that see three different example of doing the same problem. So for example, we want to simulate the aerodynamics of flapping foil, which means either pitching or plunging or simultaneously pitching and plunging airfoil. We can either incorporate the sliding meshes, as I have shown you in the last animation, by using arbitrary mesh interfaces. We can also use mesh morphing, where actually we need to deform an inner region of the mesh relative to the outer region. And we can also use the overset meshing strategy, where you can see the interesting thing is that we have multiple disconnected mesh components, and one mesh components actually moves over the other mesh components in a disconnected manner. That means these different mesh components do not have any connectivity like the other different dynamic mesh strategies. All right, so this is called overset meshing strategy. Now, how do we incorporate actually in OpenFOAM these meshing strategies? So in OpenFOAM, and by now you all know the OpenFOAM case structure. What are the different files that we have? We have zero folder within which we actually define the initial and boundary condition for different state variables. We have a constant folder where we keep all the data that remains constant throughout the simulation, such as mesh files. In polymesh folder, we have transport properties. And in systems, you have seen we have a control dict, we have other files such as FV solution, FV schemes. And if we want to do it a parallel computation, we need decompose par. So when we try to use dynamic meshes, we need this additional file or this additional dictionary within the constant folder, which is called dynamic mesh dict, okay, which is located in the constant folder. Now, within this dynamic mesh dict, we actually provide the information relating to what type of dynamic mesh motion we want to use. And we have to assign also a motion type, right? So whether the motion will be translational, whether the motion will be rotational, or whether the motion will not be prescribed but will be governed by the fluid structure interaction, kind of coupled interaction between the fluid and the structure, right? Now, while we want to assign this motion type, we want to assign it to a surface patch or a cell region or to the whole domain, right? So I will show you these examples. So in the previous examples, in the first example of the sliding mesh, the motion type is actually defined over a patch, which means it is defined over a surface, which is the intersection of the two mesh region, or it can actually be connected with the patch of the airfoil surface or the structure, airfoil structure. We can define our motion to this patch, which is the airfoil surface. Now, for the second example also, we have done the same. However, for the third example of the overset mesh, we can define this mesh motion or the motion type to the whole cell zone, which is basically a volume of cells marked as the overset cell zone. And we can tell that the whole cell zone will basically undergo a simultaneous pitching and plunging motion, as you can see in the third example. All right. So this is the main tip to actually apply dynamic mesh motion. But in the contrast, in adaptive mesh refinement, we need to define a refinement criterion based on a scalar field, as I said. So for the bubble rise example that you have seen in the previous training, this criteria can be differently assigned, but normally we can actually we can consider alpha water to be a scalar field to define this refinement criteria also. But there may be other ways also to do it. All right. And then the last but most important thing is the appropriate boundary condition. When you want to apply this different motion type on a patch or a surface or a body of cell or volume of cell, you need to appropriately change the boundary condition, particularly the patches where you apply wall boundary condition. It has to be a moving wall velocity boundary condition, because this tells the code of written in OpenFOAM that it will go and read the dynamic mesh dict to see what type of mesh motion has been applied, and it will change the boundary condition accordingly on the patch. Okay. Right. So as I told that this is the normal case structure without the dynamic meshing, but the only file or dictionary file that you need to apply dynamic mesh dict is the dynamic meshing is the dynamic mesh dict, which should be located in the constant folder. Right. I will not spend much time here, but these are some commands for you to check yourself. Where are these dynamic mesh motion solvers located, right? So if you go to solvers, which is located in your installation directory or project directory, and then applications, then solvers, you all know probably now that this is the folder where all different solvers are located. And if you put this command, you just grab the dynamic fvmesh.h, which is the header file for the most of the dynamic mesh motion solvers. It will show you this kind of results. and this kind of solvers which uses dynamic mesh motion. However, as I said, that this dynamic meshing strategy is not dependent on any physical model, right? Okay, so we don't have time, but you need to have a closer look. I'm not going to show you hands-on, but you can go and have a closer look into these folders, which are located in the source code folder of your installation directory. So the SRC folder or the source code folder has a folder called dynamic mesh. Within that, you have motion solvers. And also it has a different FSI or fluid structure interaction related dynamic meshing solvers, which are 6 degree of freedom rigid body motion solver. So please have a look into it. Okay. Now, how do we adjust the numerics when we use dynamic meshes, right? So as you have now, you know that there are different class of dynamic meshing strategy, and accordingly, you have to change the numerics or the solver settings for your simulation. And particularly because dynamic meshes have more stringent stability and accuracy requirements than static meshes, right? When you do a simulation over a static mesh, your volume of meshes are not changing inherently, but particularly if you do mesh morphing, your volume of the cells are getting deformed and the volumes are changing. So particularly for these, you have large displacement or deformation, and you have fluctuations in linear and angular velocity. You may have strong instantaneous acceleration. So to adjust to that, we need to accordingly change the solver settings to get a robust and accurate solution. All right. Whereas for AMR simulations, the mesh will change and the cells will become smaller and smaller. Hence, the cell volume will also become smaller and smaller. So if you know the stability criterion um, uh, for the standard conventional CFD solution algorithms is the current number or the CFL number, and it is proportional to delta T, which is time step divided by delta X, which is local cell size. So if you know that if your cells become smaller and smaller, your CFL number will also change from one refinement to other refinement locally, which is quite critical to get a robust and accurate solution. So we have to accordingly change it. And it is extremely important to control the CFL number for the stability of the schemes, right? And we have to keep monitoring the mesh quality, and particularly for the morphing meshes. And accordingly, we have to change the correction loops in our solution algorithm. And we have to change, we may have to remesh our problem if we get negative cell volumes, right? And we don't need to mention this. You should all be intuitively understand the dynamic meshing cases are unsteady. All right. And you have to also take this into consideration when you choose your solver settings. And of course, they are computationally more expensive. And so with this background in mind, I will quickly show you the first two. One is mesh morphing, another is overset method in a brief detail, and then I will give you some glimpse about the other dynamic meshing strategies. Now, mesh morphing is also known as mesh diffusion or mesh smoothing technique. And as I have already shown you one example of flapping airfoil where we give predefined body motion. So mesh morphing technique can be used for predefined body motion, as well as it can be used for coupled fluid structure interaction cases. So first we will see some cases of predefined motions, and then we will actually see some fluid structure interaction cases. Now, the predefined body motion can also be given in OpenFOAM in two different ways. One way is to use the well-defined continuous functions like a sine omega t, a cos omega t, where your body moves in a linear oscillation in a sinusoidal fashion or co-sinusoidal fashion, etc. Or if you want to predefine your body motion in a different arbitrary way, which does not represent any continuous function, we can also do that. We can actually move the body in a chaotic fashion the way we want, or in a random fashion with a pre-generated random variable. In that case, we have to use an input table, and we have to actually give the coordinates with the time for a particular control point on the body, right? For example, center of gravity. And we have to give the linear displacement and angular displacement as a function of time in a tabular form. So these are the two ways. Now, this I've already said that with morphing meshes, large displacement with large time step will likely result in very low quality meshes, or you will get a negative cell volume errors in that case. And we have to actually tweak the time step accordingly to get a considerable range of CFL number. And we have to see that the maximum CFL number should not exceed the convergence criterion of the CFD schemes that you are using, and according to the order of accuracy of the schemes. Now, when using mesh morphing, the solver will report the mesh quality, and one needs to monitor the mesh quality while the simulation is running. Now, let's see some examples visually so that you get the idea. I've already told you that, within the dynamic mesh dict, we can use a predefined function. And for that, we have certain syntaxes like that. So in the left-hand side, you can see the mesh with a cylinder. This is a very simple benchmark problem. The cylinder is moving up and down with the translation motion. And for that, we have to know first, what is my mesh motion library? Then within that, we have motion library in OpenFOAM. And then we need to know what type of solver we need for implementing the mesh motion. Normally, we had to solve a cell center Laplacian for the motion displacement. So we can use different solvers, but one type of motion solver is displacement Laplacian, which actually incorporate the morphing of the mesh. And within that, we have different models. One model of diffusivity is inverse distance, for example, which is called mesh diffusion method. And then within that, we have to actually mention the patch or the boundary which we want to move, right? Like, for example, here, the moving boundary I've named in my meshing as cylinder. Now, are they the only option? No. OpenFOAM has already different types of libraries for all these cases, different mesh motion library, different motion library, different motion solvers, etc. So these are some examples which you can easily find out from the source codes or the solver folder of OpenFOAM. So we have multiple such options for all these methods. And you should try and compare the accuracy and robustness for particularly high displacement problems to see which one suits your problem the best. Now, this comment is very useful to check the mesh motion, whether it is incorporated in an appropriate fashion. Is the comment is move dynamic mesh with no function object. If you use this motion, it does not solve your governing equation, but it only replicates how the mesh motion should be based on the dynamic mesh dict, which is easy for you to quickly check that the functions you are using, whether it's appropriate for your problem or not. All right. Now, coming to the predefined continuous function. So this type of function has, again, different options, but one type of option is oscillating displacement. These are inbuilt motion functions in OpenFOAM, where we give the amplitude and the rotational frequency omega. And then it understands that it is the amplitude, like A sine omega t. A is the amplitude, omega is the rotational frequency, and the body is moved accordingly. All right. And in the boundary for that cylinder patch where we are applying this motion, we need to apply this boundary condition, which is moving wall velocity. Right. So we have to change everything, every solution, every scheme. But I think by the restriction of the time, I'm not going in details of that. But this is, again, an animation showing you by applying that amplitude and frequency, what type of mesh motion we see. So you can see that this is a mesh morphing approach with a predefined continuous inbuilt motion function. All right. Now, the second type where we want to prescribe a motion, but we do not have any particular continuous functions to incorporate that, we can include this type of tabular form where it shows that the first number 5 is actually the number of time steps. And then the first 3 is the linear displacement. And the last 3 is the angular displacement with as a function of time step, right? So you can see that in this example, it at time step equal to 1 second, of course, if we don't mention any scaling, it goes up 2 unit in the linearly, then it goes positive x-axis 2 unit, etc., etc. So whatever you give in the tabular form, you actually can incorporate. See, first it goes up, then it goes right, then it basically follows whatever linear displacement you give with your time. So this is very useful when you do not know the function of the motion of your body. So you can give it in a tabular form. All right. Now, the comparison of different diffusivity function, right? I told you that when you solve this displacement Laplacian solver, that means you are indirectly solving a Laplacian equation to identify the mesh displacement points in your different time steps as the body moves. You can use different diffusivity function. So the previous one I showed is inverse distance. If we change that diffusivity function to exponential with exponential coefficient of 0.6, your mesh will move in this way. So this is also important, what type of diffusivity function you are using for mesh morphing. And these are the all different options that you can use, all right, as your motion solver. And within that, yes. So no. Okay. So I don't have these total list. I can share you. So basically my point was that it's not only these two options, there are multiple other options which are not there in my slides. So you should try with different diffusivity models to check how your mesh deforms. All right. And that has a lot to do with your robustness of the solution. Now, my next example is multiple bodies. When you have multiple bodies, can you incorporate mesh morphing or not? And the answer is yes. So in this case, we have cylinder 1 and cylinder 2, and both cases, we are giving oscillating displacement, but we are giving a different amplitude and the same omega. And you can see it moves in these two cases, it moves like this for two different inputs. All right. However, mesh morphing is not an appropriate choice of dynamic meshing strategy when you have multiple bodies, and which is very intuitive that if you have two bodies very close to each other and they wants to deform the mesh in an opposite direction, your non-orthogonality and skewness of the mesh cells will increase, and at some point it will cross the tolerance value and your solution will diverge. All right. However, if you set the parameters, you actually theoretically can do it in mesh morphing, but the best solution of doing it would be using overset mesh that I'm coming in a minute. Right. So this is another example of doing, which I've already shown you, to do a tandem airfoil, where we can define one patch as airfoil downstream, another is airfoil upstream, and we have used different type of diffusivity methods. However, if you change the interfoil distances and make it smaller and smaller, at some point your solution will actually may diverge due to the non-orthogonality of the cells. All right. Now coming to the fluid structure interaction, as you all know that the fluid structure interaction is a coupled phenomena where we do not prescribe the motion of the body, but the fluid forces actually induce a motion on the body, and in turn the body motion induces a different pressure difference and fluid forces, and it goes in a coupled manner where we have to solve the Navier-Stokes equation to get the aerodynamic or hydrodynamic forces, And then we have to apply these forces to calculate the displacement through a structural governing equation, etc. And then should be coupled either in a weakly partitioned approach or a strongly partitioned approach or monolithic approach, whatever it is. Uh, right. So this is probably clear to you. And for that, our motion solver is different. This is rigid body motion solver. We have a separate class of motion solver library, which is live rigid body mesh motion.so. This is the executable name. So we have to choose a different motion solver to direct our boundary condition to accept changing it, and the type of the boundary condition will be calculated, right? So every time step you have to calculate your boundary condition. All right. Can you all hear me? Yes, no, maybe?
Yes, sir. You can hear it.
All right. And Professor Roy, if you are there, can you tell me how much time I have?
You are audible.
How much time I have?
It is 5:13. I think take few, maybe 5 minutes.
Okay, all right, sure. So I will quickly go into the overset meshing technique and then conclude my presentation. All right.
Yes, sir. Yes, sir. Sir, excuse me. Hello.
Yes, go ahead.
Yes.
Go ahead.
Right. So as opposed to the mesh morphing method, we have another meshing technique, as I've already demonstrated to you, which is overset meshes. And this is particularly useful for multiple body motion, where you have multiple n number of different bodies which are undergoing very much high displacement in the neighborhood. Then how do we incorporate this problem? So the best example, I think of it as that if you want to simulate a freely falling flat plate, you just leave the flat plate from a height and let it settle. So this is a very complex problem because this is a fluid structure interaction problem which has multiple non-dimensional numbers such as Galilei numbers, Reynolds number, its non-dimensional moment of inertia, mass ratio, etc., which can decide the dynamics of the free falling plate, right? So if we want to do it by mesh morphing, we will not be able to do it. And another example might be if you have n number of cylinders undergoing vortex-induced vibration in the neighborhood, can we do it in the using mesh morphing approach? The answer is no. Your solution will inherently diverge. So to incorporate those fluid structure interaction phenomena with multiple bodies, overset meshes are very much useful. And then, as I said, that overset meshing strategy involve different component meshes and which are all disconnected but moving on the overlay of each other, such as for this example, we can do the same cylinder movement problem by having three disconnected mesh component. One is the cylinder mesh, which is a volume of cell which incorporates the cylinder boundary. We can have a refinement cell zone around that to get more higher resolution of the flow field, and we can have a background mesh in the background. However, then how do we transfer the flow field variable data from each components? The only way of doing is using appropriate interpolation techniques. And inherently, when we use interpolation techniques, it involves interpolation errors. So in terms of accuracy, overset meshes are comparatively lower accuracy as compared to mesh morphing or arbitrary Lagrangian Eulerian approach in that sense. Now, overset patches can intersect each other, but it adds numerical diffusion, and to capture the resolution of the flow at the overset patch is very difficult, and it needs appropriate interpolation technique to actually overcome this issue. And the trick or tip here is that you have to keep the cell size at the surface of different component cell zones similar so that the interpolation error becomes low and you get accurate solution. All right. Now, what is the architecture of the overset meshes? It is designed by two different type of cell zones. I would skip this. Here you can see that multiple component of the cell zones are present, and we have to first mark them with different zone IDs so that our solver understands first which is my primary component mesh, which is my refinement mesh, and which is my background mesh. However, the interesting concept here is this, that we have architecture wise, we have three different cell types in overset zone. One is called hole, which means that there is no solution done. And one is basically we can ignore the solution within the whole region, such as within the cylinder portion, because we are interested on the external aerodynamics of it. And then the next is interpolated at the overset surfaces or overset patches, as you can see, where interpolation happens. And the other, this kind of cyan color region is the calculated, where we directly calculate or solve the governing equation. All right. And to do all this, we actually have two different types of cells in the interpolated region. One is donor cells, another is acceptor cells. That means the data is calculated in one type of cell and is then interpolated to the another type of cells. So in that sense, some cells are donor cell and some other cells are acceptor cells. Now, what are the different type of interpolation techniques? So we have different interpolation techniques to exchange this information between different component meshes. One is cell volume weight, another is inverse distance, another is least square, and they all have different type of accuracy in terms of spatial and temporal accuracy, but this has to be mentioned in the AP schemes, that which type of interpolation technique that you want to use. All right. And if you want to get a detailed information about interpolation and everything, you can use a debug switch in the control dict, and you have to make overset as 1. So it will give you a detailed information about your calculations in your log file. Right. So these are two actually examples of prescribed motion and FSI or vortex induced vibration of the cylinder using the overset mesh motion. And I think you can understand here that we apply this motion to a cell zone in contrast to a patch, which we used to do for mesh morphing. And so here, another interesting feature of OpenFOAM, I'll just mention that it is called linear driven motion, where we can actually move a refinement zone along with our body to get higher resolution by applying linear motion to a background refinement mesh. Right, so that's all I wanted to cover. I will give you another glimpse of the moving meshes. So this is an example. For example, if you want to simulate the sloshing problem, we can actually move the whole volume of mesh, giving a 6 degree of freedom prescribed motion. As you can see here, like a tank moving with fluid with different motions. So this is called moving meshes. Then we have arbitrary mesh interfaces, which I already explained. Here we have to change the boundary type to cyclic AMI, and they have to be having connected to the neighboring patches of stator AMI and rotor AMI in these cases. And the last one is adaptive mesh refinement, which I will not describe because you have seen it for the multiphase calculation. What are the settings? So here, as you can see, the field based on which the refinement happens is alpha dot water, and we have to define what is my refinement level, what are the buffer layers, etc. What is the maximum cells I want, etc. But the interesting thing is that you can also do adaptive mesh refinement based on a derived quantity, such as here, we want to do the refinement to capture this vortex setting, right? So, and we have to find a quantity like magnitude of the gradient of u, right? Because you know what is the relationship between velocity and vorticity. So we can actually write our own code within OpenFOAM to calculate a derived quantity and then refine our mesh according to that quantity. So this is the GitHub link where this development has been done for gradient AMR. And thank you everyone. And I'll try to answer a few questions in the chat box. And I think I'm super delayed. So with that, I close this training session.
Thank you, Professor Bose. And let us see what are the questions in the chat box. Okay. It starts with Are there any examples? Yeah, can we incorporate AMR along with overset mesh? Does multiple connected mesh component means syncing criteria of background mesh and overset mesh? Can we include incorporate AMR along with overset mesh? And what
So,
is a multiple disconnected mesh criteria?
so I mean, this development has not been done yet, as per my knowledge in OpenFOAM, by incorporating AMR with overset mesh. But theoretically, I do not see any difficulty in doing that, but a new development has to be done. But I may not be aware of new developments which has been done on this. And does multiple disconnected mesh component mean syncing criteria of background mesh and the overset mesh? Yes, the syncing criteria is nothing but the interpolation. So one thing probably I did not mention explicitly, that the boundary condition for this overset meshes has to be overset in your zero folder. So when you mention the overset as the patch boundary condition, it automatically knows that it has to interpolate the field variables from one component mesh to other, which is basically donor and acceptor. And that's how the solution is synced. Now, based on your interpolation error, there can be discontinuity between the different two component meshes, which we need to overcome through appropriate solver settings.
Okay, the other question is, how do you know if the mesh volume is going negative?
I mean, you will see it in your log file when the solution will diverge. I think you can print it, even all the statistics by using debug switches, and you can see that why your solution has diverged. It can either be showing as floating point exception, and it can also show you in the log file that you have got cell volume and what is your skewness, non-orthogonality, etc.
So there is one question about time step calculation for rapid acceleration, for bodies with rapid acceleration.
Yes, that's a very, very interesting question and very important also. Like for the example, I told you that if you want to simulate a free falling plate, the moment you drop the plate, before it settles in its own dynamics, the linear and angular acceleration will be huge at the starting time step. And to actually make your solution stable, there are multiple ways of doing it numerically. The one way is to the easier way is to start with a, CFL number, which is very, very small, which will basically stabilize your simulation by accounting for the time step requirement to a very small time step, but which is not feasible to continue when your simulation gets stabilized. So you can gradually, from the start t equal to 0, gradually increase the CFL number from a very small value to a required appropriate value to stabilize your simulation. The other way is to actually do another iterations in the every time step, another correction loop to actually reduce the residuals for the rapid acceleration and then use appropriate time steps.
Yeah, there are many questions actually. FSI problem. Sorry, just a minute. Can there be multiple AMI boundary conditions? Then how to write it? I think this is more on that implementation part. Regarding flapping foils, which strategy will computationally be less expensive?
Computationally, I would say less expensive will be overset methods, depending on what type of interpolation you are using. And also it will depend on your cell size and everything, depending on your convergence. But accuracy wise, the mesh morphing will be preferable if you want more accurate solution. However, I think overset method will be computationally least expensive.
Following up the previous question on time step, for unsteady problem, is it good to start with high CFL and then reduce it, especially for vortex shading cases? Start with a
Sorry.
high CFL number and then reduce it.
For unsteady flows, is it good to start with high CFL number and then reduce it? I don't understand what is the motive
No, you
of
start
doing
with
this.
a larger time step And then as the vortex shading sets in, you reduce the time step. I think that's what he's asking for. Is it recommended or not?
I mean, it all depends on the validation and verification for the particular problem you are trying to do. Because when you start with a high CFL number, it can also give you a not so accurate value for the transition or the start of the vortex
No,
setting.
furthermore, there is always a chance of getting divergence at the beginning.
Yes, exactly. So at the start, if you don't need to
Because
change your CFL
transience is
number,
not sometimes transience is very high at the beginning, starting from
exactly.
all zero.
So the
conditions.
conventional way is to start with a lower CFL value and slowly increase it to an appropriate value which stabilizes your solution.
I think those are all. Maybe there is. If you want to move a porous body inside a stationary fluid, this is an interesting question. What type
Yes,
of machine should I go for?
This is
And there is
actually a
another
problem.
question on. Okay, first answer this and the next one.
Yeah, this is actually the problem I'm currently working on, and it's not very easy in terms of. So there is no developed available solver in OpenFOAM which can do that. So we are developing or modifying the governing equation ourselves to make a solver which can do that. But the challenge lies in terms of calculating the porous forces at the through the uh, control volume approach and transfer it to the structural solver. But we are using the overset meshing strategy to do this problem. However, you can also use immerse boundary method kind of problem to do this.
So there is another question from Multiphase. I think for bubble rising in water, we generally patch the bubble and do not use any boundary condition for the bubble. How can we use a moving mesh?
As I think already mentioned that in the bubble rising problem, we normally use adaptive mesh refinement. And for the adaptive mesh refinement, you have to find a scalar field based on which you will refine your mesh to capture your dynamics, which is normally the interface condition alpha water.
I think this is the last question. We'll take it. And if you have any further question, Professor Bose may answer it through the chat. The chat will be open. Can tabulated 6 DOF be used with multi-solid body motion solver?
Yes, for sure. I think one example I have already shown you where two cylinders are moving with different motion. So it can be always used, but depending on how close they are, your solution can diverge if you use mesh morphing.
And the last request is sharing the GitHub. I think that is.
So I will share this presentation and the case files that I have used to demonstrate this through either GitHub or a Google Drive, and I will share through a link. The link that where we'll share all the training materials, so it should contain these case files.
Okay, I think let us close this particular session and thank Professor Bose. Professor Bose is in a very short trip to India, and he came to IIT Kharagpur for logistics to meet the logistics, and we had a 2 consecutive days extensive and exhaustive workshop on OpenFOAM. So all credit goes to Professor Bose for contacting all the research persons and planning this workshop. On behalf of IIT Kharagpur and on my personal behalf, I thank him for this effort. Thank you, Professor Bose.
Thank you very much.
You
have also put equal amount of effort, so without which it would not be possible. So I'm happy that
and
it came out well.
participants are there with us for these 2 long days. One of
Yes.
them being
And
weekend in summer.
We are very glad to have 112 participants in the last
I think
session.
that the overall participation is more than 200.
Yes.
It is many of the speakers made a note that there are large number of participants, which is very good. It will be much better if all of them can take it forward, whatever we have discussed in these sessions. So we can, before we formally close it, we can take 1 or 2 comments. Of course, I have shared a feedback form, but I mean, anybody can unmute and talk about this workshop and any feedback. This is the first symposium, so then name first shows that there will be more to follow. Right? You cannot be alone first. There will be other symposiums in coming years. So we plan that every summer we'll host similar symposiums. So regarding that, if you have any suggestion, if you have any comment regarding this symposium also, for participants, I think we can hear a few of your voices.
Hello,
Please,
I'm
yes,
Sujata Singh.
please introduce yourself also.
Yeah. Hello, I am Sujata Singh, currently working at IIT Delhi in multiphase flows, CFD in multiphase flows. So I have one suggestion that in this OpenFOAM symposium, the Eulerian part or the Eulerian Lagrangian part or the DPM part is really left untouched.
Okay.
So is it would be better if one or two sessions on this could be provided for the
Are
next
you
cycle.
mentioning about ALE or Eulerian Lagrangian tracking of multiphase or for structure interaction?
No, so for Eulerian simulations for multiphase flow and
Multiphase
also
flow
the Eulerian
simulation.
Lagrangian.
Okay, we had couple of research talks today regarding which briefly touched upon that, and however, we will note it for sure. Yes.
Thank you, sir.
Anybody else wants to give such suggestions?
Hi.
Hi, Dr. Somnath?
Yes. Hi,
Yeah, this is-
hi, Dr. Vikas.
Yeah.
How are you?
Actually, I listened for all the 2 days, and actually,
Thank you very much.
Yeah, and really, this program was very interesting. And actually, you covered the wide spectrum, and actually, I think it has provided a very good material for most of the students as well as the professional also to start with that.
So Dr. Vikas
I
is
think
from CDAC, HPC CFD Divisions Directors.
Thank you, Dr.
So
Vikas.
yeah, it is very good efforts. So I hope many more symposiums, such kind of things will follow up, and it will disseminate the knowledge to the people.
Yes, I think in the coming years, we plan to do in a larger scale, maybe if possible in hybrid manner, and your support will be really appreciated.
Yeah, yes.
Please unmute yourself. Yes.
Hello. Good evening, Professor. Can you hear me?
Yes.
Yes, sir. Thank you, sir, for the amazing conference over the last 2 days. And I wanted to ask, since you are heading the BioFSI lab as well.
Yeah, my network was disturbing, but Dr. Vikas, we should take it up and try to make a physical symposium next year. And we can think in it in much detail later. Thanks.
Yes,
Yeah.
And I think besides the video lecture, also make the chat session also available if possible, because many of the discussion
Chat, I'm trying to save it. Actually, I'm trying to save the chat also so that I can share it.
Sir, so I wanted to ask, would it be possible in the future to cover topics like reduced order modeling for like aeroelasticity, considering that you've been talking about flapping wings in your
Yes,
presentation?
so yesterday we had an invited talk which by Dr. Rahul Haldar, who gave a talk on
Yes.
the machine learning models of reduced order modeling.
Yes.
These are very specific areas, and because we were limited in 2 days, so we could not fit more than this. But in the coming years, we will keep these topics in mind for sure if we
Thank you
make
so
it a
much.
larger.
Hello, sir. Good afternoon, sir. Myself, Subhashish Bosu. Sir, I have already attended two offline seminars, but I have one problem. My computer background or my laptop is not up to date, so I want to attend another offline seminar there. But I wish to get a facility if department provide me some Param Shakti or this type of computer facility there, so that I can avail this program very. I can understand it better. Otherwise, my computer and my program will be, there is a problem I am facing every time.
You write to us, and we'll inform you about the follow-up.
Okay, sir. Thank you, sir. Thank you for okay.
Okay, so if
Hi.
there are no
Hi,
further,
hi.
yes.
One more.
Yeah.
Hi, I'm Saurabh, Kumar Saurabh, and thank you, Chandan and Professor Roy, for this awesome symposium for the last 2 days. But it was really very exhaustive. So I would suggest that you please come to India for a longer period and extend this duration to maybe 4 to 5 days, if possible. Like involving the entire day in the symposium, it may be in the online symposium. It may be very difficult for, like, it is difficult for me at least. So it might be difficult for others too, hopefully. So you
Right.
can, yeah. So you can extend it
Yeah,
over
so
the
this
day.
is first time under
Yeah,
different
yeah, of
other
course, yeah, of
logistics
course. I
constraint
understand
we
that. Yeah,
arranged it. But we also realized that the schedule
yes,
has to be slightly more relaxed.
yes,
And
yes.
I know I took Professor Bose for lunch, and we really almost didn't have time to finish our lunch for as we are running for the
Mm-hmm.
next sessions. So
Yes, because
yeah.
this was the first time, we had to start somewhere and we really designed it in a short
And we
notice.
have all your mail IDs,
So,
so all the follow-up activities, not only for OpenFOAM, but also for other computational science aspects and HPC programs, you will get email notifications on that. We'll be
Yeah, yeah.
arranging few, at least this year, we'll be arranging few more
yes.
such programs.
And to make it up, actually, we have recorded these sessions. So if anybody has not been able to join, we will share the video recordings.
But I would say, yeah, it was a fantastic symposium, and I learned a lot. Actually. Thank you.
Thanks, Saurabh. All right. So any last comments before we close the session? Yes, please unmute yourself. Praveen, you want to say something?
Yeah, hello, Professor. Thank you so much for these past 2 days. It was a great learning experience. I missed a couple of talks yesterday, so I was hoping to get the recording.
It will take some time. You will get it eventually. So there
We
is some
can share
logic.
some cloud service. It'll take maybe a week to process, and then we'll share it.
Okay, thank you, professors.
Right.
Okay, formally close the session and the workshop. Thank you all for attending, and whatever the follow-up activities, for whatever reason you want to communicate with us or any of the speakers in near or late future, please write to us. Please write to any of our mail IDs or to CCDS mail ID from where you got the emails, and we'll get connected. Thank you, and I also thank once more Professor Bose for all the efforts that he has taken for that. Thank you all.
Sure. I also thank IIT Kharagpur as a whole for allowing us to organize this. And also we have supports from University of Birmingham. So, and last but not the least, thank you all to keep joined with us till the last